another edition of Subject Math. Our topic today is simple harmonic motion. Simple harmonic motion is a repetitive to and fro movement of a body about a fixed point. So here, I have an object, and my hand here is a fixed point. So if I displace this, you can see the movement. It's moving to and fro in a repetitive manner, repeating itself. So this kind of motion is described as a simple harmonic motion. Now I'm going to bring this close to the body. This is a fixed point. I'm just going to displace it. Can you see it? So I'm just going to trace out the part of the motion. This is what I have. As you can see, this is the fixed point. So it's moving this way, as you can see. So I'm going to trace this out. This is the fixed point, 0. This is my fixed point. Now, it's important for you to know that at this reading, kinetic energy is maximum, while at the other hand, the two hands, potential energy is greater, or is maximum. So if kinetic energy is maximum at the middle, that means at the edges, it should be minimum. It should be minimum. And likewise, the potential energy. Minimum. So take note of this. One very important thing about simple harmonic motion also, one of the features, is that the acceleration is directly proportional to the distance. The distance from here to here is directly proportional to the acceleration. So the motion is usually with a constant acceleration and is always directed towards the center. So the kind of motion with its acceleration is constant. And always directed towards the center. Towards the center. So the distance between this place is directly proportional to the acceleration. Acceleration is directly proportional to the distance away from the center. Now, other examples of simple harmonic motion is a pendulum bulb. When a pendulum bulb is slightly displaced, it moves to and fro. Another typical example is that of a swing. In a playground, you see the movement of a swing. It moves to and fro, while the swing is fixed at a particular spot. So this is just a sketch of what simple harmonic motion looks like. Here are some terminologies used in simple harmonic motion. The first one is a period. A period is a time taken by an oscillating body to complete one cycle. And usually, period is denoted as capital T. Period. Capital T. And is given by small t over number of oscillation. This small t is the time taken in seconds, divided by the number of the tone and flow movement, which is the number of oscillation. This time can be measured using the stop clock or the stopwatch. Then whatever gets divided by the number of oscillation will give you the period. Now, for frequency is the number of oscillation per second, the number of oscillation made by that particular body per second, and it is measured in hertz. For frequency, capital F is equals to frequency is the inverse of this. So it's just going to be number of oscillation over small t. In other words, we can just say 1 over t. So it's the inverse of the period. That will give us frequency. And frequency is measured in hertz or per seconds. Another concept is the amplitude. Amplitude is the maximum displacement of the particle from the central point. Let's say this is the central point, like that sketch we had initially. The maximum displacement from the central point. The farthest distance away or apart from the central point is known as the amplitude. In solving problems involving simple harmonic motion, here are some formulas that will be required. The first one, V is equals to W W is equals to 2 pi F, and also W is equals to 2 pi over T. W is the same thing as the angular velocity. V here is the speed. Now the R is the distance. I said that we have a midpoint. The distance away from the midpoint is the radius. Radius of distance away, and usually it's in meters. Then A is the maximum displacement from the center, which is the amplitude. So in a case where you're not given the radius, you are given the amplitude, so you just use V is equals to W. Or you are given the radius and you're not given the amplitude, you use V is equals to W. But there are cases when you have both the amplitude and you also have the radius. So in cases like that, this formula is applicable. We use V is equals to W square root of A squared minus X squared. Now the amplitude, X and R, we use them interchangeably. It denotes displacement. Anyway, theta is equals to WT. This is the angular velocity, like I said. And then W is 2 pi F. F is the frequency. T, like I explained earlier, is the period. Then for acceleration is equals to minus W squared R. So acceleration, we have minus W squared R. Don't forget that we said the acceleration is always directed towards the center. So here are some examples of simple harmonic motion. The period of oscillation of a particle executing simple harmonic motion is 4 pi seconds. If the amplitude of oscillation is 3.0 meters, calculate the maximum speed of the particle. That is V. We have to calculate V, which is the maximum speed of the particle. So the first thing we need to do is to write out our Harmonic steps. So from the question we are given t, which equals to 4 pi seconds. We're given the amplitude, which equals to 3 meters. And we have to find the maximum speed, which equals to v. So let's come here and see which of the formulas will be applicable. To find v, we need w and r. Do we have w r? No, we don't. WA, do we have WA? Okay, we have A. But to find W, what do we need? We need 2 pi over t. 2 pi, we have t. So we're making use of this and this. So our V is equal to WA. But W is equal to 2 pi over t. So we have 2 pi over t. Our t here is 4 pi. Pi cancels pi. 2 here, 2 here, 2. So we have 1 over 2, which equals to 0.5. As our W. So we have 0.5 as seconds as our W, which is the angular speed. Now, we are asked to find the maximum speed. So we are going to put this, substitute this into this formula, which is V is equal to WV. And W from here now is 0.5. Our amplitude is 3. So by the time we have multiplied this, we have 1.5 meters per second, which will give us maximum speed. Maximum speed as required is 1.5 meters per second. You can see it's as simple as that. Another example is this. A body moving with simple harmonic motion in a straight line has velocity v and acceleration a. When the instantaneous displacement x in centimeters, take note of that. Displacement in centimeters from its maximum position is given by this. T is in seconds, take note of that. So the question says determine the magnitude of the maximum velocity and the acceleration. So the first thing we do is to write out our parameters. So from the question we have x equals to 2.5 sine 0.4 pi t. So we compare this with this equation, with the equation of the progressive wave, which is a sine 2 pi ft. So by comparing these two equations, you will see that a is equals to 2.5. 2 pi ft is equals to this. our A, which is the amplitude, A which equals to amplitude, is given as 2.5. And the set is in centimeters. So we don't work in centimeters, we need to convert this to meters. So we multiply 2.5 times 10 raised to the power minus 2, and that will give us 0.025 meters. So our amplitude has been converted to meters, which is 0.025. So from here also we are given our 2 per head. Let's just compare. Let's compare this to 2 pi ft is equals to 0.4 pi t. T cancels t, pi cancels. Okay, I'm just going to leave it this way. I'm going to leave it as 2 pi f is equals to 0.4 pi. And of course, our 2 per f we know is equals to W. So we are going to say W is equals to, this is the same thing as W. 2 per f is W from here. So W is equals to 2 per f, which equals to 0.45. So I think from here we have what we need to find the velocity. We have to find the velocity, which is v. Our v is WA. We are using A because we have the amplitude. So W is 0.4 pi times A, 0.025, which equals to, we can as well write pi out. We can write out the numerical value of pi, which is 3.142 times 0.025. 3.142 times 0.025 multiplied by 0.4. That will give me 0.0314. 0.0314 meter per second. So our velocity v is equals to this. Let's find the acceleration. So now acceleration A. Don't forget acceleration from the formula I gave us previously. We said A is equals to minus W square r. A equals to minus W square r, which equals to half. W square from here is 0.4 pi. So I'm going to write minus 0.4 pi squared times r. Minus W square r, and then our r from here is 0.025. I told you earlier that we could use r or A. So in this case, we are not giving r, but we are giving A. So I'm going to use the value of A, which is the amplitude that we found previously. This value 0.025. So I'm not going to change this to A since that is what we use. So it could be this or minus W square A, depending on what you are using. So the square of this will give me, okay, it's as good as saying 3.142, which is the value of I all squared times 0.025. By the time you square the minus, it becomes plus. So we have positive, not negative. So altogether we have 0.0395 meter per second squared because it's acceleration. The unit of acceleration is meter per second squared. So our A is equal to 0.0395 meters per second squared. So I want to believe that the solution is very, very clear to us.